Hi guys, I'd like to welcome all of us to our discussion for today. So today we're going to look at different concepts under the atomic orbitals on carbon. Earlier on we had looked at the concept of hybridization of a carbon atom, and we had mentioned about the concept of SP3 hybridized orbitals, which basically is achieved from the valence electrons in the two s and the 2p orbitals which form the valence shell of a carbon atom. And from this case, of course, we had discussed on ways of representing this particular hybridization process using the energy level diagram, which showed orbitals interaction of the valence orbitals, the electrons from the valence orbitals in order to form SP3 orbitals, which of course we referred to as hybridized orbitals. And in this case, we're going to see that in the formation of these particular orbitals, the electrons which are going to form the part of the valence electrons are therefore from the hybridized orbitals, electrons which are going to be realized are going to get as far away from each other as possible. And this is in a bid to minimize the electron repulsion, which is going to be realized as we said that electrons are negatively charged. So therefore, from the laws of attraction, we're going to realize an electron repulsion. Therefore, from these valence shell electrons, we're going to see that in order for the compound to be, of course, stable due to the minimal amount of repulsion which is going to be achieved from this, there's a particular shape that this compound is going to assume in order for it to be, of course, stable in some sense. So therefore, as we had looked at the shapes of different molecules, of course, I discussed about the concept of molecular shapes in one of our videos, and that talked about the concept of a tetrahedral structure, which basically had given an example of this particular ion which is going to form, or rather this, I'll just give an example of this particular compound which is going to form a tetrahedral structure from us representing it as such, whereby we're going to have these hydrogens being given as such, and a lone pair of electrons which is going to form an orbital at this specific point, therefore trying to illustrate the tetrahedral structure. Now these molecules also from the hybridized, this carbon from the hybridized perspective is also going to form a similar compound due to the bond angle, which is going to form, of course, an angle that is going to achieve a minimal sense, in a minimal sense, going to achieve the less amount of repulsion for the electron interaction which are going to be experienced in the sp3 hybridized. Now in this case, I talked about the representation of a molecule in a three-dimensional space, and we say that we can be able to represent a molecule by using different specific illustrations. And one of them that I had mentioned, particularly on representing a compound like methane, was this particular shape, whereby I had given it as such for the hydrogens which have joined with the carbon to form this particular compound. Now, of essence for us is to ensure that for us to minimize the electron repulsion, we're going to have this angle as 109.5 degrees. And therefore, this is similarly, from this analogy, this is a similar amount of angle that is going to be, bond angle that is going to be, or rather the angle that is going to be displayed by the sp3 hybridized carbon or orbitals, which can be given as in a sense, I'm just going to have a figurative illustration of this. So therefore, these electrons, which are sp3 hybridized, are also going to have a similar illustration for this, for the tetrahedron structure given as such, whereby the bond angles is going to be 109.5. Now, in trying to display how this particular compound is going to react, for instance, in the formation of this compound of methane, therefore, this is going to have 4 electrons being added or interacting with the 4 electrons to form covalent bonds. So I'm going to have this one as, this is 1 electron, this is our one hydrogen and another hydrogen. So I'm going to have 4 of these in order for this compound to form a methane, which basically is going to be SP3 hybridized, just as we have illustrated, of course, in this particular case. So actually it's going to interact with this SP3 hybridized with this 1s 4 hydrogen atoms in order to form a methane molecule. So we can be able to represent this one still using this particular illustration, whereby we're having these 4 orbitals SP3 hybridized, having these hydrogen atoms donating an electron at each specific orbital in order to form a covalent bond. So this is hydrogens, hydrogens, hydrogens. So I'm going to do away with these hydrogens. So basically this is how this particular compound for methane is going to be formed from this SP3 hybridized carbon that we have shown in that particular case. So similarly, we're going to have a compound like ethane that is going to be realized into 2 bonds arising from the overlap of these adjacent orbitals. And this, of course, end-to-end overlap of orbitals is going to provide what we refer to as the sigma bonds. I talked about the concept of the sigma and pi bonds when I was talking on the concept of a benzene molecule, which we said is a planar molecule, of course, which consists of the sigma and pi bonds. And we had said that the end-to-end overlap of bonds is referred to as the sigma bonds, and then the pi bonds is the collateral overlap of atomic orbitals, or rather the collinear overlap of atomic orbitals that were mentioned in one of our videos. Therefore, we're going to see that for the case of this is methane, and for the case of ethene, we're going to see that there is a different illustration that is going to be given for this. And each carbon atom in the ethene molecule is of course going to be SP3 hybridized and tetrahedral in shape. But for the case of ethene, it's going to be shown that there will be a free rotation that is possible along the carbon-carbon bond, of course, which is going to form a sigma bond. And we can be able to illustrate that one using different illustrations. Either for the 3-dimensional space diagrams, we can use the ball and stick model or the space filling model. But in this case, I'm just going to use the SP3 hybridized illustration, and then for the sake of just a rotation that I've mentioned for ethane, then I'm going to use the ball and stick model in order to just drive that point. Now, from this illustration of the ethane molecule, we're going to see that the interaction between a carbon and carbon bond is going to have an overlap, end-to-end overlap, which is going to produce a sigma bond. And therefore, from this particular case, we can just be able to illustrate this molecule using the ball and stick model, whereby we have said that there is a possibility of the rotation which is going to be realized from this particular point. And now, in some cases where we were discussing about the nomenclature of ethanes, we had talked about the concept of, especially for the double bonds, we had talked about the concept of the cis and the trans. Of course, those ones are not going to be applicable here, but that one in an essence gives me the concept of rotation, which basically added the effect of changing the orientation of those particular atoms that are going to form or part of the molecule that is forming that specific structure. So in a sense, of course, we can be able to contrast this one with the methane that are given. In that, of course, we're going to have the end-to-end overlap, which is going to form a sigma bond in the ethane molecule as compared to the methane that we had seen. Now, of essence for us is to understand that the SP3 hybridized carbon is going to form a tetrahedral structure with a bond angle of 109.5 to ensure that the electron-electron repulsion is minimized. And then, of course, of essence for us is to understand the concept of a promotion of the valence share of the S2s orbital, which is promoted to SP3 orbital. And that one, in a sense, is going to open for us of course a window for understanding the bonding and the structures which are going to be achieved insofar as organic compounds are concerned. So for that we'll just stop there, and next we're going to look on a concept which is going to of course cement on this specific concept of atomic orbitals in carbon that we have seen. But I presume that this one is given us a clue on how we can be able to visualize other organic molecules insofar as hybridization of orbitals is concerned. So I'll just stop there for today. Catch us in our next video where we're going to discuss on the concept of chemical bonds and other areas which of course we might find having relevance with this specific video. So that is it for now, guys. Bye, God bless.